Hello, my name is Michael Maher, and this is Joseph and I's optimization project. To start off, a little background is that it's been proven that in nature, optical solutions happen around us. Some examples of these are how bees make their beehives. They have adapted, or either they understand calculus and optimization. They make their beehives with minimal surface area, so then they use the minimum amount of bee wax that they need. Another example is how fish and birds migrate to different places. They have learned to take the most effective and optimal way that uses the least amount of energy. So whether that's they understand calculus and optimization, they use the most optimal route, or over the past millions of years, they've just adapted to learning how to take the least energetic route. And this project specifically tests whether the canine species or dogs understand calculus and optimization. And this was done by Timothy Pennings and his dog Elvis. They went to a beach, I believe it was they went to Lake Michigan. And while Timothy threw the ball, the dog would run across the beach a certain amount of ways, and then eventually swim to the ball. And Timothy measured how far the dog ran across the beach and how far the dog swam while recording both their times to hopefully understand if canine species understands calculus, or maybe if it was some other reasons through adaptation or so what. This image represents the overview of the experiment, as the X represents the man and the dog starting in the same position, while the circle represents where the dog should end up with its target. This image also represents the many different pathways the dog could take, as it could take a directional path straight to the target, or it could run across the beach for a certain amount of time and then eventually start swimming vertically to reach its target. And the purpose of this experiment is to find out what the shortest possible time is. So part one of this project is finding the value of y that minimizes the function ty. And this is done so we can find the minimal time it takes for the dog to run across the beach and then swim up vertically to reach its target. This will be done through solving y through the first derivative test, and then a second derivative test will be performed to determine whether the answer of that second derivative test is positive or negative, which will then result in giving us our minimum or maximum value. First, so we can solve for y, we have to come up with a function of ty, because what ty represents is the shortest amount of time it takes for the dog to reach the human, and that takes into account both the running and swimming. And so in this equation, z minus y over r accounts for the rate it takes of the dog to run across the beach, and then additionally, the square root x squared plus y squared over s represents the rate it takes for the dog to swim. And since ty acts as the total amount of time and the shortest amount of time, we have to take into account both the running and the swimming, as that's how the dog will reach its target. So first, to focus on the z minus y over r, that's taking into account the dog's running rate, and z is a constant in this situation, as y is the distance the dog runs across the beach. R is the time it takes the dog to run across the beach, as we got that from our distance formula. Distance equals the rate times time, and then once we break that down, we get rate equals distance over time, and so zx is a constant, and so the distance in this situation will be our negative y, which will be how long the dog runs across the beach, as r represents the time it takes the dog to run across the beach. Also, for the swimming part of it, the square root x squared plus y squared represents, I apologize. The x is the constant in this one, as y is also the swimming distance, and st is the time it takes the dog to swim, as we got that from our distance formula. And so to get y by itself, we first take the first derivative, and to do that, we take the derivative, so we get d times dy, multiply that by the running rate, which is z minus y over r, and then we also add that to the derivative of 1/2 x squared plus y squared to the negative 1/2. And first, I apologize, I jumped a step ahead, as this is 1/2, and due to the power rule, I brought that 1/2 down, and so then you get 1 minus 1/2, which you get as a negative 1/2 over s. And then to take it a step further, I got negative 1 over r, and then I got plus 1 over s multiplied by 1/2 2y, and then x squared plus y squared to the 1/2. And I got this as that negative 1/2 exponent causes that numerator to flip to the denominator. And I got the 2y in the numerator as from the power rule, you take the derivative of what's inside the function, and since x squared is a constant, it'd be x to the second, which is 0. And then I got 2y from taking the 2, bringing it down, and then subtracting the 2 exponent by 1. And so that gave us the 2y over 2 x squared plus y squared to the 1/2. And then once I multiplied it together, the two 2's canceled out, and so I'm left with the first derivative was negative 1 over r plus y over s squared plus y squared to the 1/2. After we found the first derivative of the function ty, we can then find the critical point of that. So then that gives us the y value. We can set that to y, which will then give us our minimum point or our minimum value, which is what part 1 is looking for. So first we got our first derivative, and then we're going to equal that to 0 because we're finding a critical point of the minimum. And so first, since it's equal to 0, we can add over that minus 1 over r, so that results us in a positive 1 over r on the right side. So this gives us y over s multiplied by x squared plus y squared to the 1/2, and that is equal to the 1 over r. Our next step then is to cross multiply, which then gives us yr equals s multiplied by x squared plus y squared, and then I squared both sides, so then that could get rid of the 1/2 on the right side, which then we are left with y times r squared equals s multiplied by x squared plus y squared. Our next step is to FOIL all that, and so I put the exponents and all of it, I multiplied the s inside of the parentheses, and that gave us y squared multiplied by r squared equals s squared multiplied by x squared, and then plus s squared multiplied by y squared. And then my next step was to subtract that s squared over, or the s squared y squared over, because then this allows us to get all of our y's on one side, which will then make it easier to find y by itself. And so then after doing that, I get s to the second multiplied by x to the second equals y squared times r squared minus s squared multiplied by y squared. So then this gives us s squared times x squared over r squared minus s squared equals y squared. Multiply that by r squared minus s squared over r squared minus s squared. And the reason for this is because we first took out the y on the right side, which then led us to have y by itself as it was outside the parentheses. And so then I divided over that r squared minus s squared, so y squared can be by itself. And then after doing that, I took the square root of both sides, so then we can get y by itself, and so that square root takes away the y squared. And so for an answer, our derivative dy over, or d times y over d times t equals y equals plus or positive or negative s squared over the square root of r squared minus s squared. And then in our situation, just to go back, the r variable states for the time it takes the dog to run across the beach, and then the s stands for the swimming rate, and so we need r to be positive as the running speed. It needs to be positive because if r equaled s, or if s was greater than r, then we would get a negative number in the square root, which would not work out. And so for this case, we need r to be greater than s to result us in getting a positive number for y. And so by doing the square root, we get plus or minus. And so we know it can't be negative because we can't get a negative distance. So it's y equals positive sx over square root of r squared minus s squared. And this formula right here gives us the shortest time possible for Lacey to run across the beach while also swimming. So that gives us our most optimal time, which then will be thrown into part 2, and then part 2 will go, or then part 3 will be based off part 2. But this equation right here gives us the most optimal time for the dog to reach the person. To finish up part 1, I then performed a second derivative test, which will then give us our minimum or maximum value. to first perform the second derivative test, I took the derivative of function ty, which was negative 1 over r plus y over s multiplied by x squared plus y squared to the 1/2. To get the second derivative, I performed the quotient rule, and that got me the second derivative of the function ty equals 0 plus s times x squared plus y squared times 1 minus y multiplied by s times 1/2 times x squared plus y squared to the negative 1/2 multiplied by 2y, and we got that 2y from getting the derivative of the inside function, and since x is a constant, that's just 0. And then we brought the 2 down from the y, and then we did 2 minus 1 to get an exponent of 1. And then that got us to simplify the second derivative of ty equals s squared multiplied by x squared plus y squared to the 1/2 subtracted by s multiplied by y squared over x squared plus y squared to the 1/2 multiplied by x squared plus y squared to the 1/2 over x squared plus y squared to the 1/2. And to simplify that, we got s multiplied by x squared plus y squared subtracted by s times y squared over s squared multiplied by x squared plus y squared multiplied by square root of x squared plus y squared, and that gave us a final answer of s times x squared over s times x squared plus y squared to 3 over 2. And what this means is, by performing the second derivative test, our answer right here, or the second derivative, gave us all positive numbers. The s times x squared is a positive number, while everything in the denominator is also a positive number. The s is positive, x plus squared plus y squared. And as you can see, that results us in a positive number, meaning that it is our minimum value, which is what we were looking for in part 1. Perhaps if this was all negative, if we got a negative number, then that means that would be our maximum value. Is that what the second derivative test tells us? But since we got a second derivative of a positive, that gave us our minimum value. For part 2, Timothy Pennings and his dog Elvis wanted to try and see if dogs in the canine species really knew calculus, or if it just happened to be a coincidence that the dog may get to the ball the quickest, or they wanted to test out this theorem. So to do that, they did it. Timothy Pennings set up the most optimal way to do it, which was the dog running horizontally down the beach for 20 meters and then vertically up 10 meters. So after the 5 tries they did this, they got an average time of running 20 meters of 3.148 seconds, while the average time for swimming 10 meters was 11.464 seconds. So to do with these averages, to go back to the distance equation of distance equals rate times time, once you got rate by itself, you got distance over time. And so to find the rate of the dog running and swimming, which was what R and S stood for, R equaled 20 meters because that's how far the dog ran, and then that was divided by 3.148 because that was the average running time for the 20 meters. And that left us with a velocity of 6.35 meters per second. And then the average time for swimming 10 meters was 11.464, and so the same thing applies by using the distance equation of rate times time equals distance. After getting rate by itself, which would be the swimming rate, you do distance over time. And so in this one, the ideal one, the dog swam vertically 10 meters in the water. And so to get the swimming rate, I took 10 meters over 11.464 seconds because that was the average times of the 5 trials to get a velocity of 0.872 meters per second. And then to find out what optimally would be the appropriate slope, I then took the y from part 1, which we found, the dy over dt, and as we can go back, that gave us y equals sx over square root of r squared minus s squared. And again, r squared's got to be positive, or else it would be a negative number, so that's why r has to be greater than s, and it can't be equal to or less than s. And so plugging in these values of r and s, you get y equals, in the numerator, you get 0.872 times x over the square root of 6.35 squared minus 0.872 squared. And again, the s was just the swimming rate, and then the r's were just the running rate. And then this gave us y equals 0.872x over the square root of 39.56, which the square root of 39.56 ended up being 6.29. And so then y equals 0.8 0.72 times x over 6.29, which gives us y equals 0.139x, which would be optimally the slope that we're looking for. So for part 3 of the project, this is the actual part where Pennings and his dog Elvis performed the experiment. So Pennings and his dog Elvis went to Lake Michigan, and on that beach, Pennings proceeded to throw the tennis ball 35 times in a diagonal direction to see how Elvis would respond to chasing the ball. Would he take the most diagonal route, which is probably not the most optimal, or would he run along the beach and then a certain amount of distance and then continue to run vertically up the beach to reach the tennis ball? So after these 35 tries, we resulted in, with this scatter plot, giving us a slope of 0.1951x, or y-intercept of negative 0.3102, with the r-squared value of 0.6278. And what the r-squared value is trying to tell us is how consistent these 35 tries were, as the closer it is to 1 is the more true each point is, and how closer it is to the actual linear line. So an r-squared value of 0.6278 isn't too bad. I think there are some outliers, especially the ones at the top and maybe a few, like that far left one, right at the 5 and 1 mark. But overall, we're looking at the slope and comparing that to part 2 slope, because part 2 slope was ideally the most optimal slope. And if part 3 slope matched it, that means that Elvis did take the most optimal route, and he somewhat knows calculus. But turns out that the slope in the 35 trials was 0.195, the slope of 0.1951x. And compared to the slope in part 2, which was 0.139, it had a difference of 0.0561, which is pretty close to each other, signifying that Elvis somewhat took pretty most most optimal route here and there. And I can get into why I think that number is different in part 4. And maybe that could be because not all 35 tries were the same, as maybe the ball wasn't thrown in the same place, or maybe Elvis got tired throughout, therefore causing the times to be different, or etc. So they'll be talked about in part 4. But comparing the slope in part 3 and part 2, this does prove that Elvis did take a pretty optimal route to get the ball. And what that means is that he took the route that is usually the shortest to get the ball. So this is saying that running across the beach somewhat, or that distance, and then ended up swimming that distance, turned out to be the most, or somewhat optimal to the slope in part 2, as we found what the most optimal slope would be through using that equation in part 1 and then plugging in the rate numbers for running and swimming. And so overall for part 3, Elvis's slope was somewhat similar to the most optimal slope, therefore signifying that he did somewhat know, the dog does somewhat know calculus, but there's a lot of limitations and external factors that apply to that. But in conclusion, Elvis did take somewhat the most optimal slope to reach the tennis ball. So for part 4, this is talking about certain limitations that could have occurred in the experiment, as this could maybe explain why our slope, or the r-squared value, wasn't as close to 1 as it could have been, or why our slope in part 3 between Pennings and his dog weren't exactly like part 2, the most optimal slope. And some of these limitations occur. Could be that maybe Pennings' throw out of the 35 times wasn't in the same spot every time. And if that happened, then let's say Pennings and the dog starts here, and one ball goes here, that's the water. The dog would run a certain long distance around, or the dog would run a certain distance across the beach and then swim up to the ball. But let's say Pennings throws the second ball, and maybe it's a little closer, and he doesn't realize, or that would cause the dog to run a shorter distance and swim a different distance, which would cause the results to not be as true as they could have been. So it's the first limitation, saying that maybe the ball that was being thrown was in the same spot every time, which would cause the dog's times to be different and not true to its true value. And kind of going along with that point, another limitation could have been when Pennings would have thrown the ball, maybe he landed it in the right spot, but maybe the waves in the lake caused a ripple, causing the ball to move. Again, which would be causing Elvis's time to be thrown off a little bit. Therefore, maybe that explains why some of the slope in part 3 wasn't the same as part 2, because maybe the throw wasn't exactly where the most optimal position like it was in part 2, as part 2 was talking about the most optimal slope for the dog to take. And in conclusion, we did this experiment in this project to figure out if animals know calculus or optimization. As I said, there are examples with the bees and the fish and the birds. Whether that could be because they know calculus, I'm going to assume that they don't. Same goes for the dogs, with the canine species, because dogs, they can't speak English. They really can't comprehend a lot, I feel like. And so I'm going to take assumption that they don't know calculus, but the dog ended up taking somewhat of the most optimal route, which is pretty impressive. And so going back to that, some other limitation could be if the dog was too tired, this could cause the dog to run a lesser distance or swim more, or maybe he swims less and runs more. And even if he's more tired, he's going to run and swim slower, as he's not going to be at his peak energy. And I believe Penning said that this was a 3-hour experiment. So I mean, over the span of 3 hours, the odds of the dog getting tired are I think, somewhat high. And so I'm going to assume that Penning does not know calculus, and the canine species doesn't. Even though this may have he may have taken the most optimal route, maybe due to adaptation throughout the years, figuring out millions and millions of years ago what's easier to swim and run, and just kind of how the canine species has evolved like that. As I'm going to say that they don't know calculus, as this example shows that they somewhat do, but I'm going to assume that they don't, because they don't speak, they don't comprehend, they don't really do anything. At least I know my dogs don't. And so I'm going to come to a conclusion that the canine species does not know calculus, even though it does take the most optimal route, or somewhat of the most optimal route, as the slopes are different. If the slope in part 3 and part 2 were similar or the same, then that means every time the dog Elvis did take the most optimal route and most precise route. But in conclusion, I'm going to end with that the canine species does not know calculus, as they really can't comprehend a lot. They can't speak. They usually can't walk or do etc. stuff like that. So thank you.